So here I want to show you how economic growth worked in the Industrial Revolution. We start off with a little bit of capital. I've used a dollar sign. It doesn't have to be financial capital. It could be natural capital. By natural capital, I mean trees, soil, running water. These things nature provides for us. And we can start with a little bit of capital. Go ahead and hit that. When we invest that capital, again, we begin to produce things. We might produce, for example, maybe we're grinding corn, or we're producing grain, or we're making ships, or we're producing firewood. When we produce a little bit of something, we might make a profit. The profit accumulates more capital. We use more capital to invest in larger production processes, and we capture economies of scale. Economies of scale means as things get bigger, they get cheaper. Hit that again. Another thing that we do in the Industrial Revolution in order to reduce costs is specialization of labor. So productivity goes up, costs go down. When costs go down, you accumulate more capital. Keep going, and we'll see where this cycle leads to us. Economies of scale and specialization of labor lead to increased efficiency, cost reductions, more profit. Hit it again. More profit or reduced cost leads to increased sales. Keep going. And we can see how we create this virtuous cycle. And then you use that profit to build a bigger factory. What do you get from a bigger factory? More production at less cost. That's critical. Larger means cheaper. In two ways. Cheaper because sometimes bigger is just more efficient, and because you can often divide the tasks up and make them increasingly more specialized. This is the way growth worked in the Industrial Revolution. So we're going to take a look at some energy industries and see what kind of examples we have. Keep going. And again. One thing that's happening in renewable energy is wind turbines. The larger the wind turbines get, the less costly they are. So we keep building these things bigger and bigger and bigger in order to make them more efficient, bring costs down, reinvest the capital in additional research and bigger factories, bigger turbines. We see exactly this playing out. Let's go to the next slide. This shows us how wind is doing in the United States. Hit the pop-up. South Dakota is now drawing, when I say now, I'm talking 2011 data. So as of 2 years ago, South Dakota was drawing 22% of the state's electricity from wind power. I think that's remarkable, because we talk about how much penetration could renewables really have in the grid, and we know that solar is not a very big portion of the electricity that we're using right now. But if you go to certain states, I mean, there's Montana at 4.2, but certain states get very high penetration right now. And it's interesting that South Dakota is so high for wind, because South Dakota is also tied to the fossil fuel industry. Let's go to the next slide. This is what's happening in PV costs. You might be familiar with this slide. We can see that the produced silicon PV modules are in blue. Show us some animation on that. However, hit the, again, yeah, here we go. In 2005-2006, we had a global silicon shortage. The silicon PV industry was growing very quickly. Silicon prices, instead of coming down according to the experience curve that we just showed worked with wind, and we just showed worked in this virtuous cycle called the Industrial Revolution, they stayed elevated. So market forces can sometimes perturb what I was suggesting was this virtuous cycle of increased efficiency. That elevated silicon price as a result of the shortage allowed First Solar to enter the market with CadTel cells. And First Solar undercut the silicon prices because they weren't dependent upon silicon, and grew rapidly. Once the silicon shortage was over and they brought new silicon production online, we see those prices collapse. The blue line just falls off the cliff right down into the same valley where we've plotted the hurricanes Katrina and Rita. Now, this is not on the x-axis. This is not time. Time does move forward to the right, but it's experience. So if you go back and erase those pop-ups, we'll take a look at the units. Cumulative global capacity in megawatts of wind, including onshore power plants in Denmark, the USA, and PV. So we can't superimpose our historical or our chronological understanding. The point is that the virtuous cycles that I've showed you aren't based upon time, they're based upon how much production. Production equals profits, profits equals capital investment equals greater production. Okay, good. Let's go to the next slide. You'll have to click 3 times. Yeah, keep clicking. This is a different look at the PV module experience curves, and we can see they're coming down. We should be familiar with that in this audience. Keep going. It shows where first solar enters. Now I want to show you what happens when this virtuous cycle breaks down. In order to do that, we're going to have to look at a mature industry. The mature industry is coal-fired electricity. On the y-axis, we have efficiency. You probably know that the first generators sold by Thomas Edison were incredibly inefficient. They were installed in Manhattan, and they got something like, well, I don't know, here in 1900, it's estimated at 3%, and I think that's about right. 3% efficiency, that is to say, 3% of the energy going into the generator is actually produced as electricity at the point of use. That's terrible. The improvements in technology and the increase in the size of the plants improved that efficiency up until, again, we see this inflection point in the 60s, and we're getting about 33%. Go ahead and hit the button. There's 2008, when we can no longer run this virtuous cycle of economies of scale result in cheaper costs and larger production. What does that mean for the U.S. economy? What it means is the end of growth. I showed you a model of growth on which the Industrial Revolution was predicated. And it requires increasing economies of scale, increasing specialization of labor. If you can no longer extract cost reductions from that model of growth, then you no longer grow. Now that's not exactly the case for the electricity industry in the United States. They have grown, but they've grown very modestly. They haven't grown exponentially. And they've been growing because the population has been growing. One kind of growth, industrial growth, that's going to stop. It needs to be a different kind of growth if we're going to extend this Industrial Revolution model. Keep going. Terrific. Now here what we're seeing is a transition from one fuel input, one energy input to the economy to another. This graph starts at 1800, goes all the way to 2000. In the beginning, and by the beginning I mean 1800, the American economy was fueled by wood and animal feed, and to a much lesser extent coal. The very first locomotives, they ran on wood. And they used wood like you would not believe. So they had to cut down whole forests just to run these inefficient wood-fired locomotives. Thank goodness that they switched to coal, which is a more dense fuel, more abundant than wood, or we would completely have denuded North America of trees. So you see, wood is in decline, decline, decline. Animal feed, however, is in ascension until about the mid-19th century. So we get to the late 1800s, we get to the about 1900, and we're no longer running the economy off of animal feed. So we see wood and animal feed in decline, coal in ascension, until somewhere we see oil is beginning to take over. Oil undergoes this exponential increase. Natural gas, exponential increase. And then we see electricity, but in this case, I've only flagged electricity from hydropower, nuclear, solar, wind, geothermal, not electricity that's being produced from coal. What you see is these energy transitions. Each time, a lower quality energy source is superseded by a higher quality energy source. This is another way that the economy moves forward because we're using higher quality energy inputs. Go ahead and hit that button. Something happened. Wood went down and it never came back. Animal feed went down and it never came back. Coal went down, but then around 1970, it made a comeback. So in the 60s, there were a lot of predictions about how nuclear was going to be the next big thing. It never happened. It sort of got shut down. And coal instead increased. Let's go to the next slide. So this is what we need to know in order to understand where in that previous cycle we are with energy technologies. This graph shows us the energetic return on investment. Remember I said Colonel Drake, he dug a well in Pennsylvania, oil comes out. It takes energy to make energy. Just like it takes energy to run the manufacturing plant that produces PV modules, you have to invest energy in order to run the drill rig, or in order to build the nuclear power plant, in order to mine the uranium, in order to extract the natural gas. So if you're at the top of this graph, you have a little bit of energy input. That's the small arrow going into the well or mine. You create the well or mine and you get a ton of energy out. So the thick arrow moving to the right is the energy exported. A little bit of energy needs to be invested back into the mine. So we might have a coal mine that's producing coal, but it uses trucks and shovels that all run on diesel fuel. So a little bit of energy in, a lot of energy out. That's usually what happens when a new energy technology that's very profitable starts. It has a high energetic return on investment. And by energetic return on investment, I'm looking at a life cycle basis. When we get down to B, now we take a massive energy input and we get just a little bit of extra energy, a little bit of surplus energy to export. This is where corn ethanol is right now. We need to use fertilizer. That takes energy. We need to run tractors and plows and equipment. We need to plant the seeds, run the pesticides and the herbicides, harvest the grain, move it to the ethanol production facility, run the ethanol production facility. That takes a lot of energy. And what do we get out? A little bit more energy than we input. So there's something even more circular about where we are on B. So then we go down to C. In C, the energy inputs exceed what we're able to export. We're putting more energy into this so-called energy technology than we're even getting out. All right, so we need to understand how energetic return on investment works in order to evaluate where on the previous curves we're going to find ourselves with those energy technologies. Let's go to the next slide. This is how we calculate it. Remember I showed you that product life cycle diagram that showed you have to invest in order to make sales. In order to make profit, you have to develop a product. Well, here we have to put energy into the construction. And that's all investment. Once power generation starts, we're able to sell power to the consumers. Now, we still might consume some energy. We still might have to run our plant off of electricity or diesel fuel or something like that. But what we're selling to consumers is profitable. It exceeds the energy that we're using. Then we have decommissioning. That takes energy again. So it's the same kind of financial flow diagram that I showed previously, but now it uses energy flows. We calculate the energetic return on investment by taking what's exported, putting that in the numerator, subtract the use, and put it over the amount of energy that we consumed in construction. I hope that makes some sense. Let's move forward, take a look at some numbers. This is the energy payback time in years, and we're taking a look at PV silicon versus CAD-TEL again, and we see different silicon technologies have different energy payback times. What do I mean by energy payback time? When do you produce enough electricity to recoup all the costs incurred in production of the module? CAD-TEL, again, a shorter energy payback time. According to this graph, we get the energy invested back out in under a year. Let's go forward. Now, this is going to show us lots of different energy technologies. Over on the left-hand side, we have energetic return on investment that's very high. So the x-axis is sort of backwards. We go from 50 down to 2. The rich technologies are on the left part of the graph, the poor technologies on the right. So these historic oil and gas fields, they had very high energetic returns on investment when they were first discovered. We move from there, as we deplete the highest quality resources, we move from there to new oil and gas fields. And we can see a decline in energetic return on investment is moving from the mid-40s down to the high 20s. Solar PV occupies this enormous range between, say, 30 all the way down to 10. Sugarcane, ethanol, tar sands, nuclear. And there's our corn ethanol. I warned you that it wasn't very good. It's in between, well, 1 and 2. Let's go to the next slide. We're going to take another look at energetic return on investment. Now, this is from Cutler Cleveland. This whole concept was developed by Charlie Hall, Robert Kaufman, and I've extracted this from a paper that Cleveland and co-authors produced. It shows energetic returns on investments for different technologies. Way up at 100, we have crude oil 1930. That's on the left-hand side of the graph. Move right next to it, crude oil year 2000. We've moved from an energetic return on investment from 100 to 20. Why? If you have to build a $1 trillion ship called an oil rig, float it out to the Gulf of Mexico, and discover oil 2 miles below the surface of the ocean, it's going to take a lot of energy. That's a lot harder than poking a hole in West Texas and letting the oil just rush up out of the gushers that were discovered in the 1930s. So our energetic return on investment has gone way down because it takes a lot more investment in order to extract the same amount of oil. Let's look at coal. Energetic return on investment 1950, 100. By 2000, down to 80. But we don't really want crude oil, and we don't really want coal. What we really want is things like gasoline and electricity. So there's going to be further losses in the system. And again, we see corn ethanol, oil shale, coal liquefaction, fine. Hit the button. We're going to see what happens. There's the decline in energetic return on investment due to using up the high quality resources. Hit it again. Same thing with coal, decline in high quality resources. Hit that again. But if you compare crude oil 2000 to gasoline right now, well, now we're not measuring the energy in crude, and the numerator now is gasoline. Well, there are going to be losses in the refining process as well. So the real energetic return on investment on what we put in our cars isn't 20, it's more like 10, 12, 8, 15. There's some uncertainty. Great, hit it again. When we take into account the losses in energy due to generating electricity and transporting it to the point of use, we see that our energetic return on investment for coal isn't 80, it's more like the low 20s. So consistently we're getting this message from fossil fuels that we need to be somewhere between 10 and 20. That's where fossil fuels are for energetic return on investment right now. Hit that again. Here's where solar cells are. If solar cells could power your car, then this would be competitive with gasoline. Right now they can't. Gasoline is a better energy source than solar cells are. So I agree. Solar cells not competitive with gasoline, and it looks like coal-fired electricity still has a better energetic return on investment than solar cells do. This isn't a financial comparison, this is a thermodynamic comparison. Hit that button again. Now we go to wind turbines. It is competing with coal. Coal's a better source in some cases because the wind you can only use the electricity when the wind is blowing. But the energetic return on investment at many wind sites is comparable to coal. Hit that again. Here's the Alberta tar sands. Competitive or not? No, the energetic return on investment is too low. So somebody had a great quote, and I wish I could remember who said this, but they said trying to get crude oil out of the Alberta tar sands is like trying to extract crude oil from your driveway, because it's all locked up in rocks. It's very thick and viscous. You need to hit it with steam and natural gas and upgrade it. By the time you're done with all that energy investment, your energetic return on investment is down there with, well, I'm not going to say corn ethanol because that's so bad, but it's down there below solar cells. All right, hit it one more time. There's fracking. Now, fracking didn't used to be up there. When this graph was done, see how where they say oil shale? When they were counting the oil that you could get out of shale deposits, that's not what are called tight gas plays necessarily. But now we're able to extract oil and natural gas from the rocks that exist in the Marcellus Shale and other areas of the United States. Fracking has a future thermodynamically. We're up in the 50s, high 50s, maybe high 40s. So this is higher than any other energy technology that we have right now on energetic return on investment. Remember that I said that typically when a new resource becomes viable, it starts with a very high energetic return on investment and then declines. If you were investing in energy, would you be investing in wind, Alberta tar sands, solar cells? What would you pick? Now this isn't an economic graph, this is merely a thermodynamic graph. Fracking is likely to be in ascendance. Remember I said we needed to understand energetic return on investment in order to understand the previous graph that shows which energy sources are going to grow and which are going to decline. That we go progressively from what's moved the economy forward is we start with these low quality fuels like animal feed and wood, and we move to higher quality fuels. The ones that are more dense and more flexible. Well, here, when an energetic return on investment begins to decline, we can anticipate that costs will go up, and that will incentivize the search for substitutes. Fracking looks like a good investment. If they can solve the environmental problems, it's likely that we'll see a lot of money made in fracking. So there's very little historical data on fracking, but they've been doing fracking in Pennsylvania for, for several decades. It's just now the fracking combined with horizontal drilling has opened up lots of possibilities. There's data from one county in Pennsylvania called Indiana County where someone has calculated the energetic return on investment. It's already declined over the last 15 to 20 years to about half, a little bit more than half than what it originally was. The rate of decline of energetic return on investment in fracking is faster than the rate of decline that we've seen in coal or any other technology. Fracking is giving us, energetically speaking, a little window, about 20 years of energy production. And when the 20 years are over, fracking will be a mature industry with a low energetic return on investment, just like the other fossil fuels. What are we going to do with our 20 years? This is exactly my point. You have 20 years to get this right. And if you don't start building solar cells now, There is no way we will have the energy infrastructure that we need 2 decades hence already in place. It will be impossible to cover the rooftops and parking lots with enough solar cells fast enough if we don't start now to prepare for the next energy transition that's happening. Now, most of you are young enough to think that in 20 years you'll be in mid-career. If you buy this slide, what are your careers going to look like? Thinking further ahead, maybe solar and wind is where the young people want to start their career. And they can leave the fracking to the people who are already in the energy business.